So here's an example for the single stage softening. So the problem is to first find lime. So the ash, carbon dioxide, dosages for recarbonation, solids production for selective calcium removal, and to develop a bar graph showing the original theoretical species in the water. So here is the given. The following table presents the concentration, equivalent weights, and milli-equivalent weights of all species analyzed. And one note is that residual calcium in water is equal to 30 milligrams per liter as a CaCO3 or 0.6 milliequivalent per liter. So here is the bar graph of the raw water for the example. The figure is a bar graph showing the theoretical combination of chemical species in the raw water. Carbon dioxide is placed to the left of the bar graph if present. Cations are always placed at the top of the bar graph. Calcium, magnesium, sodium, and potassium are shown in this order. Anions are shown at the bottom of the bar graph and should be separated as follows: hydroxide, carbonate, bicarbonate, sulfate, and chloride. The water should be electrically neutral, so the concentration of cations must balance the anions. If not, the water analysis is suspect. So, lime addition will be required for the neutralization of carbon dioxide according to equation, and for the conversion of calcium bicarbonate to calcium carbonate according to equation 6.74. Non-calcium carbonate hardness can only be removed by precipitating with sodium carbonate according to equation 6.79. So the final hardness of the water is calculated as follows: 0.6 milliequivalent per liter plus 1.9 milliequivalent per liter times 28 milligrams of CaO milliequivalent per liter, and the answer is 70 milligrams CaO per liter. So where does this 0.6 come from? It is from the given of 0.6, and for the 1.9 it is from here. So for the soda ash dosage, 2.2 times 53 is equals to 173. So for the next is the carbon dioxide dosage. First stage recarbonation will be required to stabilize the water. Assume a CaCO3 concentration of 30 milligrams per liter in the effluent from the settling basin, in that 50% of the carbonate is converted into bicarbonate, resulting in an equilibrium concentration of 15 milligrams per liter of CaCO3. So, for the equation, 15 times 1 over 50 times 22 equals to 6.6 milligrams per liter. So for the solids production as CaCO3 can be calculated by 0.6 plus 1.9 plus 2.2 minus 0.6 all by times 50 is equals to 205. So bar graph of finished water is based on the following concentration of ions. So here is the finished bar graph. Data here are from the concentration of ions that was calculated in here. So this is the finished water bar graph. So after the single stage softening, we are now discussing to the two-stage excess lime soda ash treatment. So first stage recarbonation. It occurs to convert excess lime CaOH2 to CaCO3 in a solid state and to lower the pH to around 9.5 to 10. This also resolubilizes some of the suspended MgOH2 in a solid state, resulting in a maximum magnesium concentration of 20 mg per liter as MgOH2. Soda ash is added to the water for removing calcium non-carbonate hardness. Second stage recarbonation. It involves adding more carbon dioxide to convert some of the soluble CaCO3 to CaHCO3-2, which lowers the pH to approximately 8.5. This stops the precipitation of CaCO3 in a solid state and produces a stable water. Split treatment. Softening using the split treatment scheme involves treating a portion of the raw water by excess lime treatment, then blending this softened water with the remaining portion of raw water bypass. Using split treatment allows the municipality to achieve any desired water hardness above 40 mg per liter as CaCO3. Split treatment can lower overall treatment costs due to smaller reactors and reduce chemical costs. This is used for removing additional magnesium hardness, and the carbon dioxide is used for neutralizing the excess lime. When the treatment objective is magnesium removal, a material balance of magnesium can be performed to determine the ratio of the raw water that must bypass softening. The ratio of the bypass flow to treated flow is determined using the following equation. So, ratio of bypass flow fraction is equal to magnesium concentration in raw water final minus magnesium concentration in raw water in a soft form all over magnesium concentration in the raw water minus magnesium concentration of the soft water. So here's an example for the excess lime soda ash softening problem. Problem is to calculate the lime and soda ash requirements to achieve the practical limits of hardness removal given the following water analysis, and to develop bar graph showing the original theoretical species in the water. Assume that excess lime treatment in a two-stage system is being used. So here is the table. The following table represents concentration, equivalent weights, and milli-equivalent weights of all species analyzed. So here is a bar graph showing the theoretical combination of species in the raw water is presented below. So it represents this. The following table presents also the theoretical species. Excess lime treatment is assumed. So the total lime dosage as CaO assuming 90% purity is the sum of all species in column 4. So 4.32 times 28 times 8.34 times 1 over 90 is equals to 1120. Where mg denotes millions of gallons, the total soda ash as Na2CO3 assuming 85% purity is the sum of all species in column 5. So 1.02 times 53 times 8.34 times 1 over 0.85 equals 530 pounds per mg. On the first stage carbonation determined by multiplying the sum of the excess lime added plus remaining magnesium hydroxide concentration. So 1.25 plus 0.2 times 22 is equals to 31.9. Second stage recarbonation. For example, if this is 50% conversion of the calcium carbonate is assumed to be converted to calcium bicarbonate. 0.5 times 0.8 times 22 mgCO2 is equals to 8.8. Solids or sludge production. The solids or sludge produced during softening estimated by summing up column 6 and 7 Column 6 represents calcium carbonate solids, while column 7 represents magnesium hydroxide solids. So, for the computation, CA03 solids is equals to 0.45 plus 3.6 plus 0.2 plus 0.82 minus 0.60 times 50 is equals to 223.5 mg per liters. CaCO3 solids is equals to 223.5 times 8.34 is equals to 1,864. So, for MgOH2 solids is equal to 0.82 minus 0.20 times 50 is equals to 31 milligrams per liter. And after 31 times 8.34 is equals to 259 pounds per mg. So, for the computation of total solids procedure is 1,864 plus 259 is equals to 2,123. So, the bar graph after lime and soda ash addition is shown below. The bar graph of the finished water is shown the final graph. And for the fourth subtopic, other softening methods. Ion exchange is another technique used for removing hardness from water and is extensively used in households. Calcium and magnesium ions are replaced by sodium ions by passing water through a kaolinite or morellinite bed or synthetic material such as polymeric resin. Softening can also be accomplished when water is passed through a semi-permeable membrane such as those used in reverse osmosis, ultrafiltration, or other membrane process. So that's all for water softening. So we'll be discussing now mixing and flocculation. Mixing. Dispersing coagulants into the water is a critical step in the treatment process sequence. Mixing of chemicals may be accomplished by turbine and propeller, mechanical mixers, over and under coupling, inline mechanical mixers, inline static mixers, and by injection into the suction intake of a pump. The velocity gradient is one of the main parameters used in designing mixing systems and is determined by the following equation. Velocity gradient is equals to quantity power imparted to the water per volume over absolute viscosity of the water raised to 0.5, which is equals to quantity power imparted to the water over absolute viscosity of the water times volume of the basin and all over I raised to 0.5. For the flocculation involves slow stirring or mixing of the stabilized colloids to promote particle aggregation and removal during subsequent settling operations. Mixing cannot be too intense as the fragile flux will share into smaller fragments and not settle properly. Paddle wheel flocculators and vertical turbine mixers are the primary types of devices used in water treatment. Paddle wheel flocculators rotate from 1 to 5 rpm, whereas vertical shaft turbines rotate from 10 to 30 rpm. First, paddle wheel flocculators. Paddle wheel flocculators may use horizontal or vertical shafts, but typically, horizontal shafts are preferred at conventional water treatment plants. A detention time of at least 30 minutes is recommended, with a flow-through velocity no less than 0.5 feet per minute, and no greater than 1.5 feet per minute. In recommended standards for waterworks, engineers are encouraged to use tapered flocculation to produce large, dense floc. Tapered flocculation employing 3 separate compartments, each at a different velocity gradient, is normally practiced so that a dense, good settling floc is produced. Typical G values used in the first, second, and third compartments respectively are 50, 20, and 10 seconds. The velocity gradient varies from 10 to 100 per second, and the GR parameter varies from 104 to 105. The power dissipated in the water by a paddle flocculator is calculated by power dissipated in the water is equals to coefficient of drag times area of paddles times density of water times velocity of the paddles relative to water raised to 3 all over 2. Normally, 0.70 to 0.80 of the paddle velocity, the velocity VR of the paddle blade is calculated by velocity of the paddle blade is equals to 2 times pi times distance from the center of the shaft to the center of the blade times rotational speed with a unit of revolutions per second. Second, vertical shaft turbine flocculators. In new water treatment plants and those that use direct filtration, vertical shaft turbine flocculators are typically used. This type of flocculator has an impeller attached to a vertical shaft that is rotated by an electric motor. These are different types of impellers that produce either radial or axial flow mixing. Important design parameters of these types of flocculators include power number, effective thumb diameter, and diameter to effective tank diameter ratio. The power number is calculated by power number is equals to power input over fluid density times rotational speed raised to 3 times impeller diameter raised to 5. The effective thumb diameter is determined from effective thumb diameter is equals to square root of 4 times plan area of the compartment over pi. The D over TE ranges from 0.3 to 0.6, but a value of 0.4 to 0.5 is recommended. So we have here an example for mixing. Question. Determine the dimensions of a rapid mixing basin to process 3 mgd of water. The basin will be square and the depth is assumed to be 1.5 times the width. Use a detention time of 30 seconds and velocity gradient of 750. The average minimum sustained temperature is 40 degrees Fahrenheit and the absolute viscosity is 3.229 times 10 raised to negative 5 pounds-feet square. 2 rapid mixing basins will be constructed, each having the capacity to process the entire flow. Determine the following. A. Dimensions of L, W, and D. And B. Power input with the unit of horsepower. Solution Part A. Calculate the volume of the rapid mixing basin by rearranging the detention time equation. So, volume to basin is equals to R times Q is equals to 30 seconds times 3 times 10 to the power of 6 gallons over day times 1 day over 24 hours times 1 hour over 3,600 seconds times 1 feet cube over 7.48 gallons is equals to 139 feet cube. So, volume to basin is equals to length times width times depth is equals to 139 feet cube. Since L is equals to width, or area is equals to width squared, and D is equals to 1.5 times width, we'll be able to have a equation of volume to basin is equals to width times 1.5 width equals to 139 feet cube. So, width is equals to cube root of 139 feet cube over 1.5 and equals to 450 feet. And W is equals L, so length is equals to 4.50 feet. For D, 1.5 times 4.50 feet, so we were able to solve 6.75 feet of depth. So for the solution part B, the power input is calculated by rearranging equation. Power input is equals to G squared times mu times volume of the basin. So power input is equals to 750 per second squared times 3.229 times 10 raised to negative 5 pounds per feet squared times 4.5 feet times 4.5 feet times 4 times 6.75 feet. So power input is equals to 2.48 times 10 cube feet pounds times 4 powers over 550 feet pounds is equals to 4.5 horsepower. Therefore, construct two rapid mixing basins with dimensions 4.5 by 4.5 by 6.75 feet deep. Each basin would be provided with a nominal 4.5 HP mixer. The actual horsepower would be greater than this and would be estimated by dividing 4.5 HP by the combined efficiency of the mixer and motor. So we have here an example of paddle wheel flocculation basin design. A flocculator that is 30 meters long, 50 meters wide, and 5 meters deep houses 4 horizontal paddle wheels. Each paddle wheel has 4 symmetrical arms with fiberglass boards 2 meters from the shaft to the center of the board, rotating at 1.5 rpm. Paddles are 13 meters long and 0.20 meters wide. The water treatment plant processes 95,000 mT per D of water. Assume that the mean water velocity is 25% of the paddle velocity and coefficient of drag equals 1.5 and density are equal to 1.139 times 10 raised to negative 3 kilogram meters per second and 991.1 kilogram per meter cube respectively. So determine the following: A. Velocity of paddle blades, the unit of meters per second. B. Total power input. C. Velocity gradient. D. Detention time. E. G. Where dimensionless. So solution part A. Velocity of paddle blades is equals to 2 pi r times n is equals to 2 times pi times 2 meters times 1.5 rev per minute times 1 minute per 60 seconds, which is equal to 0.31 meters per second. So for the solution part B, velocity of the paddles relative to water is equals to 1 minus 0.25 times velocity of the paddles is equals to 0.75 times 0.31 meters per second, which is equals to 0.23 meters per second. So area of the paddles is equals to 4 paddle wheels times 4 arms times 30 meters times 0.20 meters is equal to 41.6 meters squared. So power dissipated into water is equals to coefficient of drag times area of paddles times density of water times velocity of the paddles relative to water cube all over 2, which is equals to 379 kilograms meter squared per second cube. So power dissipated in the water is equals to 379 kilograms meter squared per second cube times 1 n over kilogram meters per second squared is equals to 379 Newton meters per second. So power dissipated in the water is equals to Newton meters per second times 1 joule over n times 1 over joules per second is equals to 379. So solution part C. So velocity gradient is equals to power imparted to the water per unit volume over absolute viscosity of the water raised to 0.5, which is equals to power imparted to the water over absolute viscosity of the water times volume of the basin raised to 0.5. So 379 Newton meters per second over 1.39 times 10 raised to negative 3 kilograms meters second times 30 meters times 15 meters times 5 meters all raised to 0.5, which is equals of velocity gradient of 12.2 per second. So solution part D, R is equals to volume to basin over Q is equals to 30 meters times 15 meters times 5 meters all over 95,000 meters cubed per day times 24 hours per day times 60 minutes over hours is equals to 34 minutes. So for the solution part E, velocity gradient times R is equals to 12.2 per second times 34 minutes times 60 seconds per minute is equals to 2.49 times 10 to the power of 4. So now we will be discussing about sedimentation. For sedimentation, there will be three subtopics, which are free settling, flocculent settling, and ideal settling basin. So sedimentation. Gravity settling or sedimentation is the major unit operation used for removing suspended solids. Sedimentation is considered a unit operation involving solids-liquid separation using gravitational force. If the raw water contains turbidity greater than 1000 NTUs, pretreatment in the form of plain sedimentation is typically accomplished before proceeding to coagulation and filtration processes. So there are two types of settling that are typically encountered. These are free settling and flocculent settling. So first, free settling. Observe when there are discrete, non-flocculent particles whose size, shape, and specific gravity do not change time as they settle. Particles settle as individual entities, and there is no interaction between particles. Examples of free settling include grit and sand particles in grit removal systems and plain sedimentation of surface waters. The terminal settling velocity of a particle will be discussed by me later these sections. So first, there are three factors that act on a particle as it settles: gravitational force, buoyant force, and drag force. As a discrete particle settles, the particle will accelerate until drag force equals the difference between the gravitational and buoyant forces, at which time a constant settling velocity will be achieved. So, gravitational force minus buoyant force is equals to drag force. Next, gravitational force is equals to mass density of the particle times acceleration gravity times volume of the particle. Next equation is buoyant force is equals to mass density of the water times acceleration gravity times volume of the particle. Next equation is drag force is equals to coefficient of drag times cross-sectional area or projected area of the particles in direction of flow times mass density of liquid times settling velocity squared all over 2. Next, for spherical particles, the volume and cross-sectional area are calculated by first, volume of particles is equals to pi times d cubed over 6, while cross-sectional area are computed by pi times d squared all over 4. Next, when the Reynolds number is less than 1, laminar flow conditions exist and CD is calculated by CD is equals to 24 over NR. During transitional flow between laminar and turbulent, NR is equals to 1 to 104 and CD is determined by CD is equals to 24 over NR plus 3 over square root of NR plus 0.34. The coefficient of drag is assumed to be equal to 0.4 for turbulent flow when Nr is more than 104. So for the second subtopic, flocculent settling. Flocculent settling occurs in primary clarifiers and during settling of coagulated water into wastewater. As flocculent settling particles settle, their size, their shape, density, and settling velocity will change with time. Newton's law or Stokes' law cannot be used for modeling flocculent settling. For the computation of percent removal is equals to quantity initial concentration of species minus final concentration of species times 100 all over initial concentration of species with a unit of milligrams per liter. For calculating the overall percent removal of solids may be achieved at a given detention time. So, RT or total suspended solids removed at a given detention time is equals to ISO percent removal line intersecting the time axis at a specific settling column depth or RO plus quantity summation of difference between adjacent ISO percent removal lines times distance from top of settling column all over total depth of settling column. So for the flocculent settling laboratory procedure, flocculent settling column analysis are typically performed in a clear PVC column with sampling ports spaced approximately 6 inches or 15 centimeters apart. A column on the order of 5 to 6 feet or 1.5 to 1.8 meters is used. Steps involved are 1. Fill settling column with coagulated water to be tested. 2. Take an initial sample for SS determination. 3. Take samples from each sampling port as a function of time. 4. Calculate the percent SS removals and plot them as a function of time and depth. 5. Calculate overall percent SS removals using equation 6.27 for the several detention times. And lastly, 6. Plot overall percent SS removals versus T or detention time. So the next topic is filtration. For filtration, we will be discussing two subtopics, which is grain size characteristics and filter hydraulics. Water filtration is a process for separating suspended or colloidal impurities from water by passage through porous medium, usually a bed of sand or other medium. There are several methods of classifying filters. One way is to classify them according to the type of medium used, and another common way is by a allowable loading rate. Loading rate is the flow rate of water applied per unit area of the filter. It is the velocity of the water approaching the face of the filter. To solve it, phase velocity is equals to flow rate onto filter surface over surface area of filter. Based on loading rate, the filters are described as being slow sand filters, rapid sand filters, or high range sand filters. So for slow sand filters, as the suspended or colloidal material is applied to the sand, the particles begin to collect in the top 75 and to clog the pore spaces. As the pores become clogged, water will no longer pass through the sand. At this point, the top layer of sand is scraped off, cleaned, and replaced. While for the rapid sand filters are cleaned and placed by forcing water backwards through the sand. This operation is called backwashing. So for the first subtopic of filtration, which is grain size characteristics, the size distribution or variation of a sample of granular material is determined by sieving the sample through a series of standard sieves. So one such standard series is the US standard sieve series. It is based on a sieve opening of 1 mm. So, grain size analysis. The grain size analysis begins by placing the sieve screens in ascending order with the largest opening on top and the smallest opening on the bottom. A sand sample is placed on the top sieve and the stock is shaken for a prescribed amount of time. At the end of shaking period, the mass of material retained on each sieve is determined. The cumulative mass is recorded and converted into percentages by mass equal to or less than the size of separation of the overlying sieve. Then the cumulative frequency distribution is plotted. Geometric mean and geometric standard deviation. The parameters most commonly used, however, are the effective size, or 10 percentile, P10, and the uniformity coefficient U, or ratio of the 60 percentile to the 10 percentile, or P60 over P10. Use of the 10 percentile is the use of the ratio of the 60 percentile to the 10 percentile as a measure of uniformity was suggested by Alan Hazen. So for the next subtopic of filtration, which is about filter hydraulics. So the head loss that occurs when clean water flows through a bed of clean filter media is an important design value to determine the overall head required to operate a filter. The flow through a clean filter of ordinary grain size at ordinary filtration velocities would be in the laminar range of flow depicted by the Blake-Cosenzi equation that is dimensionally homogeneous. So for the Blake-Cosenzi equation, head loss in depth of bed B is equals to dimensionless Cosenzi constant times dynamic viscosity of the fluid times 1 minus E squared all over mass density of the fluid times acceleration of gravity times EQ times squared of grain surface area per unit of grain volume. So for the next topic, we'll be discussing about disinfection. Disinfection. The last treatment step in a secondary plant is the addition of a disinfectant to the treated wastewater. The addition of chlorine gas or some other form of chlorine is the process most commonly used for wastewater disinfection in the United States. Chlorine is injected into the wastewater by automated feeding systems. Wastewater then flows into a basin where it is held for about 15 minutes to allow the chlorine to react with the pathogens. There is a concern that wastewater disinfection may do more harm than good. Early U.S. Environmental Protection Agency rules calling for disinfection to achieve 200 vessel coliforms per 100 ml of wastewater have been modified to a requirement for disinfection only during the summer season, when people may come into contact with contaminated water. There were three reasons for this change. The first was that the use of chlorine and perhaps ozone causes the formation of organic compounds that are carcinogenic. Second was the finding that the infection process was more effective in killing the predators to cysts and viruses than it was killing the pathogens themselves. The net result was what the pathogens survived longer in the natural environment because there were fewer predators. Third was that chlorine is toxic to fish. Next topic is the absorption. Adsorption is a mass transfer process wherein a substance is transferred from the liquid phase to the surface of a solid where it is bound by chemical or physical forces. Adsorption is considered for removal of SOCs, VOCs, and naturally occurring organic matter such as DHM precursors and DBPs. Generally, in water treatment, the absorbent or solid is activated carbon, either granular or powdered, at activated carbon. So what is PAC and GAC? PAC, or powdered activated carbon, is fed to the raw water in a slurry and is generally used to remove taste and odor-causing substances or to provide some removal of synthetic organic chemicals, while GAC, or granular activated carbon, is added to the existing filter system by replacing the anthracite with GAC, or an additional contactor is built and is placed in the flow scheme after primary filtration. The design of the GAC contactor is very similar to the filter box, although it is deeper. All about PAC. Biologically derived earthy musty odors in water supplies are a widespread problem. Their occurrence interval and concentration vary greatly from season to season and is often unpredictable. As mentioned, one of the most popular methods for removing these compounds is the addition of PAC to the raw water. The dose is generally less than 10 milligrams per liter. Advantages and disadvantages of PAC. First, the advantage of PAC is that the capital equipment is relatively inexpensive and it can be used on as a needed basis. Second, but the disadvantage is that the absorption is often incomplete. Sometimes even doses of 50 milligrams per liter are not sufficient. For GAC, as an alternative for taste and odor control, many plants have replaced the anthracite in the filters with GAC. The GAC will last from 1 to 3 years and then must be replaced. It is very effective in removing many taste and odor compounds. Generally, GAC is used for SOC removal either as filter media replacement or as a separate contactor. Some uses of GAC. GAC has been proposed to be used to remove natural occurring organic matter that would in turn reduce the formation of DBPs. It must operate in a separate contractor. Since the depth of a conventional filter is inadequate, GAC has also been considered for removal of THMS. However, the capacity is very low and the carbon may only last up to 30 days. GAC is not considered practical for THM removal. So for the last topic of chemistry water treatment, membranes. What is a membrane? A membrane is a thin layer of material that is capable of separating materials as a function of their physical and chemical properties when a driving force is applied across the membrane. In the case of water treatment, the driving force is applied by using a high pressure pump and the membrane type is selected based on the constituents to be removed. In the membrane process, the feed system is divided into two streams, the concentrate or reject stream and the permeate or product stream. The membrane is at the heart of every membrane process, and it can be considered a barrier between the feed and product water that does not allow certain contaminants to pass. More about membrane. There is a pressure drop across the membrane called the transmembrane pressure or TMP that must be overcome by the water feed pump. The performance or efficiency of a given membrane is determined by its selectivity and applied flow. The efficiency is called the flux and is defined as the volume flowing through the membrane per unit area and time. The selectivity of a membrane toward a mixture is expressed by its retention R and is given by retention R is equals to contaminant concentration in feed minus contaminant concentration per mate all over contaminant concentration per mate times 100%. The value of R varies from between 100% or complete retention and 0% means no retention. Membranes can be described by a variety of criteria including 1. Membrane pore size, molecular weight, cutoff, membrane material and geometry, targeted materials to be removed, type of water quality to be treated, and/or treated water quality. Along with these criteria, membrane processes can also be categorized broadly into pressure-driven and electrically driven processes. A brief description of pressure-driven membrane processes. So first, reverse osmosis. Reverse osmosis is the process that's traditionally been employed for the removal of salts from brackish water and seawater. It depends upon applying high pressures across the membrane in order to overcome the osmotic pressure differential between the saline feed and product waters. Next, nanofiltration. This process, also called membrane softening, lies between RO and ultrafiltration. This membrane process employs 500 to 1000 kPa for operation. While it provides removal of ions contributing to hardness, the technology is also very effective for removal of colored and DBP precursors. Next is ultrafiltration. Ultrafiltration membranes cover a wide range of MWCOs and pore sizes. Operational pressures ranges from 7 to 700 kPa depending on the application. Tight ultrafiltration membranes may be employed for removal of some organic materials from fresh water, while the objective of loose membranes is primarily for liquid or solid separation, example particle and microbial removal. Next is the microfiltration. A major difference between microfiltration and loose ultrafiltration is membrane pore sizes. The pore of microfiltration are approximately an order of magnitude greater than those of ultrafiltration. The primary application for this membrane process is particulate and microbial removal. So that's all for my report of chemistry of water treatment.